on Friday. And I've got a few more to cover with you. Have any questions about the homeworks? Anything at all? Those are ones that I didn't give you solutions to. I just gave you the homework problems, and they were effective. They're good problems. No questions about them? Did you do them? You didn't. Okay. Oh, that's nice. I mean, I don't know what you got going, but I'm going to tell you those problems are a little more challenging than Stu's problems, and not only that, they only give an answer, not a solution. Did anybody do it? You did. Tried. Which one did you not get the answer?
Did you do the first one?
Okay, you gotta help me here.
Consider a lossless half-wave dipole antenna if the antenna is delivering 1 milliwatt.
Okay, hold on. This is a dipole antenna, and it's got a power that's being transmitted at 1 milliwatt?
Yes.
All right, 1 milliwatt. Okay.
Determine the received power if the load is changed to 10 ohms.
Oh, this is a perfect problem. This is the kind of problem I like. Let me recreate the problem. It's this. They've got a halfway. What's with these markers? I've got a half-wave dipole as such, and they've got a load that they attach, and the load is, what is it now?
10 ohms.
Just 10? They want to know if the actual power received by the antenna is equal to 1 milliwatt. They want to know what the voltage or power is at the load. Is it voltage or power?
Received power.
All right, they want to know how much power is received by the load, right?
Yes.
All right. Now, please follow me on this. This is the kind of problem that catches people off guard when they get it on my test. So they want how much power is actually received by the load. So first, you have to take a look at how, in the, last lecture we did this too, how we model this antenna. When power is coming into this antenna, and you're receiving 1 milliwatt, what it's assumed is that there's some theoretical open circuit voltage that we can actually calculate. And then there's the antenna impedance. Well, the impedance is going to be equal to, if it's the half-wave, it's 73 ohms, 73.2 ohms, plus J 42.5 ohms. Now that is internal. All this is internal. So it would be something that would be related to the actual wire itself of the antenna. Now, when they talk about P received as 1 milliwatt, they're saying if this was into a matched load, and you remember a matched load would have the same real component, 73.2, but the inductive portion would be minus J 42.5, so it would cancel. This would allow the maximum power to be received. Do you all remember this, class? Now what I'm going to do is just get rid of this imaginary part and simply leave this and call it R rad, the radiation resistance of the antenna, and this would be R rad. And this is assumed the configuration where we're talking about a maximum received power of 1 milliwatt. It's in this configuration. Do you follow me? Now the key is this. What we're trying to determine is the open circuit voltage there, because if we can determine the open circuit voltage, then no matter what load I plug in here, I can just use circuit analysis techniques to get the power. Make sense to everybody? Okay, so how do I do that? Now I can say that V open circuit, right, squared over the resistance would be 2R rad times 1/2 that would actually be the maximum power received. You don't remember talking about this? Please, if you have calculators, do this with me this one. I wanna make sure you guys get the right answer that I provided. People mess these things up, and I'm not sure why, but it seems inherent to a lot of the stuff people do. So when I look at the V open circuit here, and remember that's the peak voltage, V open circuit would be the square root of 4 times the radiation resistance times the power received. That means V open circuit would be equal to the square root of 4 times 73.2 ohms times P received, which is 1 milliwatt, right? So that's 10 to the minus 3. So tell me what the V open circuit is.
0.541.
Okay.
0.541.
Keep that in your calculator, 0.541 volts. And that's peak volts, by the way. It's not RMS. That's VOC. Now, if that's y'all with me on this so far? Everybody? Now what I'm gonna do is say, well, to figure out how much is gonna be received by that load, I go ahead and I put the proper circuit for the antenna, the actual effective circuit. So I have plus to minus that V open circuit. I'm gonna leave it as just V open circuit. Then I have 73.2 ohms, and I have the J42.5, and then I put my 10 ohm on. So then I go ahead and I put a resistor here that's 10 ohms. And I want to see how much power is received by that resistor. Well, you can do it a number of ways. I'm just going to go ahead and calculate the voltage across that resistor and say the power received by that resistor would be 1/2 the magnitude of that voltage squared divided by the resistance. Does that make sense? So I'll calculate the voltage across that resistor, and that means V on the load would be equal to V open circuit, which is, what is it, 0.541. So it's 0.541. And then it's going to be times the actual resistance, 10, over 10 plus this, or it'd be 83.2 plus J42.5. And that would be the actual voltage. Could you give me the magnitude and forget about the angle, just give me the magnitude of that. Do y'all agree with me? Is there a test there or something?
I got 57 millivolts.
Fifty-seven point nine.
Yes, sir.
Call it 58. How's that? Anybody else? All right. So that's the voltage at the load. Now, what's the power at the load? Power at the load is 1/2 magnitude of voltage at the load squared over the actual resistance of the load, in my case. So it's 1/2 times that, 58 times 10 to the minus third, squared divided by 10. That should be the power, and hopefully it'll agree with what he has. What do you get? Anybody?
microwatts.
Yeah. Or 0.
168. What does he have for the answer?
0.336.
Point what?
Milliwatts. 0.336 milliwatts.
That would be times 2 to that.
Yeah, but this is milliwatts, right? Does it say milliwatts? If that's milliwatts, then when we look at this, P received is going to be 1/2 V open circuit squared over 2 times the radiation resistance, right? I mean, this is the total resistance. The normal way to say power received would be 1/2 V squared over R. Well, the total resistance is 2 times R rad. So that means this would be P received times 4 times R rad times square root. Is this number right here? Is that right? Oh, it's right.
Yeah, that's what I got. Yeah.
And this number's right?
Yeah, that is also right. Oh, yeah.
Well, that makes absolutely no sense.
Wait, isn't it 1/4 VL squared over RL? Or is that just for the RRAD case?
This is the voltage right here, unless there's something I've done wrong here. This should be the voltage across this point, right?
Yeah.
Well, it's that voltage we're squaring to get power.
Right.
So if we take that voltage and square it, and divide it by the resistance, which is 10, and then by 1/2, because in fact that's not an RMS voltage, that's a peak voltage. That should be the right answer. If he has twice that value, there's an anomaly. There's nothing else in that problem? It's extremely strange, because I've done these problems. Wait a second, does he say, read the problem again?
Consider a lossless halfwave dipole antenna. If the antenna is delivering 1 milliwatt to a max load, determine the received power if the load is changed to 10 plus J0 ohms.
He could be saying it's not an exact half-wave dipole, it's cut down to 0.485. Remember 0.485 lambda, then it gets rid of the reactive component, do you all remember that? Now that's a possibility, do this for me. If this goes away, I'm just curious about this. That means if that goes away, then this would be the actual voltage, right? So just give me that voltage. That's what it's cut down to 0.485.
So 65 volts?
Is that what it is?
Yes.
65 times 10 to the minus 3 volts. Then take 65 times 10 to the minus 3, put it in here.
And you get 0.21
Alright, so it's not that either. That might be a mistake in the book. And I'll tell you, I'm not sure about this, but that could have been one of these 1/2 things that he forgot to put there. It's exactly half of what we calculated?
Yeah.
Alright. Well, then I'm going to venture to say that, what was this, 50? And I'm going to say that they probably forgot the 1/2 right here, because if you look at Wentworth's book, and this is, he shows this on 461. Only it's got a cut down antenna, that one. Hold on for 1 second. Oh, I'm sorry, this is 483. You're gonna see how he has P received equal to V open circuit squared over 4 times the radiation resistance. That's this right here. So 4 RRAD P received is V open circuit. That checks this box. I think it's wrong. I think his answer's wrong by a factor of 2. It's off by a factor of 2. So, another one. But this is a big problem. Because you could easily see how what you could do is have a transmitter here, right? A given gain and stuff like that. Then you could have a receiver here. put a different load on, and tell me what voltage is at the load. Now you'd have to understand how to first get the power incident on this, then you have to calculate the power received, the ideal power received to get the open circuit, and then you would have to plug in the load to that to see how much power is delivered. All right, that'd be a good problem. How about the next problem? Because I think I give you a series of problems that all were like this.
Ask a question real quick.
Mm-hmm.
It says, that 1/2 P received is equal to VL squared over 2ZL.
What's that?
It says 1/2 of P received equals VL squared over 2ZL, which means that P received is VL squared over ZL. If the received, if it's matched.
Where are you looking?
That same page.
43.
Equation 8.12.
Cause it was matched, wasn't it?
No, 10 ohms was there. Remember,
Oh.
he put 10 ohms. That's the idea. He put a resistance that is not optimized for maximum power transfer. If it's maximized for maximum power transfer, exactly half the power received is dissipated in the load. The other half is re-radiated. There's a mistake. It's a factor of 2. Glad we did that one. All right, what about the next problem that I gave you?
The maximum effective aperture of a half-wave dipole operated at 300 megahertz.
All right, this is, so the frequency is 300 megahertz. And they want the aperture, right? Is that right?
Maximum effective.
All right, well, aperture is always going to be lambda squared over 4 pi times the directivity, or really the gain. Now, for a half-wave dipole, do you remember what the gain was, anyone? Maximum gain.
For halfway, 1.64.
That's exactly right. For a short dipole, it's 1.5. Half-wave, it's 1.64. So this would be 1.64 for the gain over 4 pi, and then times the wavelength squared. Well, at 300 megahertz, that's 3 times 10 to the 8. C over F would be 1, correct, class? The wavelength would be 1 meter. That means 1.64 over 4 pi should be the maximum aperture. What do you get for that? Just to make sure his answer for this one is consistent.
0.131.
0.131 meters squared. Is that what he had in the answer? Okay, check that box. We might as well do them if you didn't, to make sure you know how to do them. What about the, because there's no solutions for these. All right, these are just answers. What's the next one?
An antenna on an aircraft is being used as an electronic countermeasure to jam enemy radar. The antenna has a gain of 12 dB in the direction of transmission.
Gain of transmitters, 12 dB? Okay.
And the transmitted power is 5 kilowatts. Determine the electric field intensity in the vicinity of the enemy radar, which is 2 miles away.
All right, so we've got our little jammer here. We're sending out a signal, and then 2 miles away, I want to know what the electric field is. Probably because I want to see if it's going to cause any threshold problems for some electronic device. All right, now how would you do that problem? This is a typical problem where you have to understand the basics of gain and electric field. First of all, if you have an antenna, right, and it's got a certain gain, then the power density at any point, the average power density, which I like to call SAV, because that's the pointing vector, will be equal to the actual gain of the antenna, but not gain in dB, gain linear, gain of the transmitter, right, times the power transmitted over 4 pi r squared. The power transmitted over 4 pi r squared is the amount if there was no gain, if it was isotropic. The gain sharpens it, all right? Now that's the power density. And what is that equal to? Well, if that's the power density in watts per meter squared and you're 2 miles away, you're in the far field. Do you agree with me there? Well, what's the power density in terms of E field? Do you remember? Anyone?
1/2 E squared over beta.
Right, 1/2 magnitude of E squared over eta naught for air, free space. So therefore you can take a look at this and you can say that the E field itself, magnitude-wise, would be equal to 2 times eta naught times gain of transmitter times power transmitted over 4 pi r squared and the square root of that. Does everybody see what I've done there? I'm solving for E. And the only thing I have to do is multiply that gain PT over 4 pi r squared by 2/8 and then take the square root. Now, to get the gain into a non-dB form, into the linear form, I know that gain in dB is equal to 10 times the log of the linear gain, G, right? So I put 12 divided by 10 or 1.2, take it to the power. 10 to that power, 1.2 is equal to G. Right? So then you could plug in the numbers, because take a look what you have. You're gonna have 2 times 120 pi, right? Times the gain, which is 10 to the 1.2 power, times the transmitted power, which is 5,000, over 4 pi r squared. We have to take r and turn it miles into meters. And the way I used to do it is I take 5,280 times 2, now I have it feet, and then feet to meters is times 0.3049, I think. That's the way I used to do it. Nowadays with your smartphones or Google, just look it up. I mean, just how far is it?
3,218.7.
3,218 meters? 3,218 meters, okay? Now, what does that come out to? Let's make sure we get the right equal for this one.
I'm gonna add 0.677.
Volts per meter. 0.667, did you say?
677.
677 volts per meter. Is that what you got? Is that in the book? Everybody see how you get this? This is important to do. One more? I gave you a bunch.
What is that value for the gain? What does that say?
Well, the gain in dB is 10 times the log of the gain in linear terms.
Right.
So now we need the linear gain for our equation. So the way to get this is divide the gain in dB by 10, that's 1.2, and then take both sides, 10 to that power on both sides. Do y'all follow me? Can you see in the back?
Mm-hmm.
Okay, and over there in the far back, it's important you see this. And I tell you, you can't get casual about this. This is the kind of stuff, people make all sorts of odd mistakes. All right, let's do another one, sequentially. I like these problems better. Go ahead.
The lossless half-wave dipole will be driven by a 10-volt peak, 50 ohm source. Determine the electric field intensity at a distance of 10 kilometers in a plane perpendicular to the antenna.
All right, wait a
Compute
second.
volt-
They have, this is driven by what now?
10-volt peak, 50 ohm source.
50, what, say that again?
50 ohm source.
Okay, so they got an internal impedance of 50 ohms here. Go ahead.
Determine the electric field intensity at a distance 10 kilometers in a plane perpendicular to the
That's maximum gain, R at 10 kilometers, and they want the electric field out here, right?
Yes.
All right, anybody want to take a shot at this?
We can find power transmitted.
You could.
Well, I guess we don't have gain, so we can't.
Oh, you got gain, it's a half-wave dipole.
Oh, that's
So gain's 1.64.
So we can find power transmitted.
How would you do that though?
Just a question. Could you just-
Let me tell you this, there's a lot of ways to do this. I'm gonna show you probably the easiest. You could, by the way, the way you do it, here's how you would find power. First, you would represent this in terms of its lumped elements. And you would say the equivalent circuit is this. I have this voltage that's plus or minus 10 volts peak. And then I have an internal resistance of 50 ohms, right?
Yeah.
Now I put in the equivalent antenna in circuit. Well, that's equal to a real resistance of 73.2 plus J of 42.5, unless it's cut down to 0.485. So there's my circuit. Now all the radiated power is associated with the power that's going to be absorbed by that element right there. Can everybody follow me on this, class? Radiation resistance is that power absorbed by that is the power that is transmitted. So if we wanted that power, how could we get it? Well, we could take and find the current and take I squared times R divided by 2, couldn't we?
Yeah.
So therefore, we could say that the total current circulating, I, would be equal to 10 over, and this would be 73 plus 5 is 100, and what is that, 123.2 plus J 42.5, and that would be a current. I'd only need the magnitude of that. If I throw these down the floor, remind me to throw them out. Y'all agree with me there? What do you, can somebody just give me that for kicks?
76.7 milliamps.
Anybody confirm that?
Yeah.
76.7.
All right, now, how much power would be associated with the radiation resistance? That would be 1/2 times magnitude of I squared times R rad, or 73.2 ohms, right? That's 1/2 I squared R, correct? And that R is the radiation resistance. Do you agree with me?
Yeah. We're at 0.215.
2.215 watts?
0.215 watts.
Oh, 0.21, thank you. 0.215 watts. Take a second, y'all get this? With me on this one? Okay. Now that I have that, I can easily get the power at this point, right here. Because now I can say that I know the average power density, PAV, at a range, which is really my SAV, is equal to the transmitted power times the gain over 4 pi R squared. Now the transmitted power is this, so it's 0.215. The gain is maximum 1.64 because it's perpendicular at 90 degrees over 4 pi, and then you have R squared, and R is, I erased it, 3,000,
R was 10 kilometers.
oh, I'm sorry, just 10 kilometers, just 10, so it's 10 to the 4 squared. Y'all agree? I can make it. I mean, are you with me on this? Give me that number too.
2.8 times 10 to the negative 12.
That's watts per meter squared. And from the last problem, how do we get the electric field from that?
That just relates to intrinsic impedance.
Remember, power, the average power is 1/2 times magnitude of the E field squared over eta. So I can say that 1/2 times magnitude of E squared over eta naught is equal to that, which is going to be, I'll just call it P av. So that means E squared, or E, magnitude of E is 2 eta naught P av square root. And you can tell me what that is, because P av is that 2.8 times 10 to the minus 12.
I got times 10 to the minus 10.
That's what I did.
Oh, sorry. I guess I didn't hear it right. 2.8 times 10 to the minus 10. Anybody else? Is that right? All right, so when you take that and plug it in here, multiply it by 2 times 120 pi, and then take the square root, what do you get? This is the correct way to do it. It's the long way, but it's the correct way.
0.46
Millivolts per meter.
Yeah.
Millivolts per meter. Is that the answer?
Yeah.
All right, now, I'm going to show you the other way to do it. It would save some time. Once y'all get caught up. This should be helpful to you. Because it's like going through a test question, bring up all my old tests and put them before me and say, where'd these go? This is sort of what we're doing. These are the tougher ones, by the way. So now, if I wanted to do it, remember, the key is this right here, the current. Once I have that current, I know that the electric field out here is given in terms of a current, right? And remember, this is for maximum gain, correct? So I know when I look at the electric field from a half-wave dipole, that was equal to J, right, times 60 over R times e to the minus J beta R times the cosine of pi over 2 cosine of theta. And it was in the a theta direction. Y'all remember this, right? And it's times I, pardon, times I. Right? You agree with me, everyone?
Yeah.
Now, if it's this cosine of pi over 2 cosine theta at 90 degrees has a value of 1. Right? You may not see it, but you can actually calculate it. If you take the cosine of theta, cosine of 90, it's 0, right? 0 times pi over 2 is 0. Cosine of 0 is 1.
Yeah.
Alright, so that's 1. Now, that means the only thing I have to calculate in terms of the magnitude is just 60I over R. The magnitude of J is 1, the magnitude of e to the minus J beta R is always 1. It's just 1 at some angle. So that means the E field can be gotten as 60I over R, which is 10 to the 4th. Calculate that for me. The I's, that value, 76.7 milliamps.
Yeah.
Yep.
0.46
Millivolts per meter. Now you notice this is a lot easier to do. It's one step. Or really 2 steps. Calculate I and then take that times 60 over 10 to the 4th.
So,
60.
so if you were looking at it at some angle, you would just plug in the
Yeah,
angle.
then you gotta evaluate that nasty.
And E is still just gonna be 1.
E to the minus J beta R, ignore when it's magnitude. The J, ignore. It's of no value. Alright?
Okay.
But I would go that route if it was me doing a test.
Yeah. So,
Yours is more complete in the sense that you calculated all these, you call it intermediate terms that may be of interest to somebody, power densities and stuff. Tell you guys one thing. I was coming in this morning, and if I leave my house and allow 20 minutes, I can usually park in that lot up by Domino's right across the street. Today I came in. Traffic's backed up so far you can't get to the lot, and I can't go down Glen because they're doing construction. So I'm thinking, I'm waiting. There's Chick-fil-A. They must have had 30 or 40 cars that were back there, and they're not moving very quick. So I was a few minutes late for class. This has happened to me coming here. When I come in and park in that lot and there were spaces getting to them, Chick-fil-A they got it as far as dragging people in there. More people go to that place than I think all the fast fooders around here combined.
I think part of it is like they have some summer camp for like little kids, like 4 or 5, like some science and math thing going on, and they take them to Chick-fil-A for lunch.
At lunch and breakfast.
So they take like 40 or 50 6-year-olds to Chick-fil-A.
My kids come walking in with Chick-fil-A all the time. My students down at the 8 o'clockers, that place is, whatever they're doing it right in a big way because, and I like that stuff too, but I'm not gonna wait an hour. I'm sorry, I don't like it that much. Huh?
They got an app, so I order on the app and we pick it up.
Just go to Zaxby's, call it good.
They have one thing there that I'm gonna tell you, it's almost sinful because it's so good. They put bacon on this chicken sandwich. Have you ever had that one? God, that thing's just.
They got a barbecue now, so it's chicken, bacon, barbecue sauce.
And I don't eat this stuff very often at all. But my God, that should be illegal. These kids are just, they're feeding junk to these kids and they're loving it. All right, next one. Oh, I hope you don't get me in trouble for that. It was a joke. Occasionally I get an email out of somebody out of the blues watching a video of mine from years ago. Why did you say that? Beats me. It just came out of my mouth. Anything?
Another one?
Yeah?
A wire carrying a 1 milliamp current.
Oh, this is a good one. Go ahead. Go ahead.
A
This
wire
is-
carrying a 1 milliamp current at 100 megahertz is parallel to in 1 centimeter from an infinite perfectly conducting ground plane.
Alright, hold on, 1 centimeter. And how long's the wire? L equal what?
I don't think it just says it's 1 centimeter from.
Yeah, but what's the length of the wire? Read it again.
The wire carrying a 1 milliamp current. at
Stop.
100
Stop. 1 milliamp current. Alright. So I equals 1 milliamp. Go ahead.
At 100 megahertz
Alright.
is parallel to in 1 centimeter from an infinite perfectly conducting ground plane.
Alright.
As shown in the figure. Determine the electric field 3 meters above the ground plane.
It doesn't give the length of the
The
wire.
length is 1 meter.
It says 1 meter?
Yeah, it
Well, it
it
shows
shows
it-
it in the diagram.
Ah, perfect. Now we're going. So L is 1 meter. Now this is the one I was talking about. Remember? I showed you guys how to do, this is a good one. People screw this up if they don't work it at least once. Alright, now, let's go through. What?
Oh, gotcha. I thought you had 2 currents, well, let me just.
No, I'm saying that's the
just
length.
Yeah, I got it.
It's the length.
I was confused.
Alright, matter of fact, I'm gonna get rid of one, because now I'm gonna put another current. And I told you to put an image down here, right? 1 centimeter down in what direction? If this is I, it's going this way.
It's going opposite.
Opposite direction. I here, right? Now get rid of the ground plane. Matter of fact, get rid of this. Now we're gonna go up 1 meter. Or
From-
3 meters or 1? Oh. Alright, so D is 3 meters, and we're gonna assume it's from the center or from the ground plane. Follow me? Please make sure you watch this. Now, I gotta figure out what the relative length of this is in terms of wavelength. So lambda is C over F, which is 3 times 10 to the 8th. Over 100 megahertz is 10 to the 8th, or 3 meters is a wavelength, right? Alright, that means if I take lambda, if I look at this and take L over lambda, I have L is 1 meter over 3 meters. So it's 1/3 of a lambda. It's not 1/2 of a lambda, it's 1/3. But let not your heart be troubled. What he meant to do is say, you know, 1.64 would be the gain, or, yeah, it'd be the gain if it was a half wave, right? But this is gonna be a little shorter than half wave, and it's in that gray area. Honestly, if you're below a half wavelength, default to the equations for a short dipole, standard rule of thumb, okay? I mean, if you're, 1/3 is quite a bit less than a half. It's not like just less than a half. 1/3 of a wavelength, you can do this, and you're gonna get a pretty good answer. So now I know the E field for a short dipole is actually J eta beta I times the length of the dipole, all over 4 pi r times e to the minus j beta r times the sine of theta. Correct, class? That's for a short dipole. I only care about the magnitude of the E field, don't I?
Right.
That means what I can do is get rid of that J term there. But let me do something. I'm gonna also say this happens at theta equals 90 degrees. And because of that, I'm even gonna get rid of the sine term, all right? Are you with me? I'm gonna get rid of the J term, because that won't have any bearing on this. So now I make the case that the total E field, E total, would be the E field from the first current element, I'll call that 1, plus the E field from the second current element. That's 2. All agree with me? Please make sure you watch this. We did this last time. So this means that if I take a look at the total, maybe I'll leave the J here just for completeness. I have J eta beta I, same I, over 4 pi r, and I'm gonna make the contention that 3 meters plus or minus a centimeter is about 3 meters when it's 1 over it, okay? So the 1 over r distance does not vary in any way, shape, or form substantially. Do you all agree with that, class? So I'm just gonna leave it as r, or better yet, leave it as 3. Now, here's where it becomes interesting. For the first one, when I have E to the minus j beta r, if you remember this is going to be e to the minus j beta, and then it's going to be r minus 1 centimeter, right? But the second one will have a minus sign because the current will be going in the other direction. Remember this from last time, class? This one, the current's going this way, we're assuming that's positive, and we're gonna have e to the minus j beta r minus this. But now the current down there is in the opposite direction, so it's minus e to the minus j beta r, and it's going to be j beta part r, and it's going to be plus 1 centimeter. I'm doing it again for a reason. Do you agree with me, everyone? Now I'm going to pull the e to the minus j beta r out in front. So I have j eta beta I over, and this is really going to be 12 times pi, if I put the number 3 in there, e to the minus j beta r, and then it's going to be e to the plus j beta times 10 to the minus 2 minus e to the minus j beta times 10 to the minus 2. Y'all agree with me? Now what do I do next? This is do you all agree with what I've done? You could actually brute force this in a calculator right there, but there's an easier thing to do. Remember what we do, guys?
Equal to negative 2j sine.
It's actually positive because that's e to the plus j here, right? You follow me? So what I can do is take this and say this is really equal to j eta beta times I over 12 pi e to the minus j beta r, and then I can say this is going to be times 2j, and then it's going to be times sine of beta times 10 to the minus 2. Now, the next point of interest is what is beta? Well, they give me a wavelength of 3 meters, right? So when I look at beta times this, beta times that, I have beta times 10 to the minus 2 is equal to 2 pi over lambda, which is 3, times 10 to the minus 2. And you can tell me what that is, because that's going to be, it's really going to be the, I don't know, somewhere around 2.5, 2.4, 2.3 times 10 to the minus 2. Anybody? Take 2 pi over 3 times 10 to the minus 2. That's
21 million.
21 times 10 to the minus 3rd. Remember, that's radians. That's very small, isn't it? All right? Remember, the sine of a small angle is a small angle? All right, if it's in radians. So now you can just do this. You can simplify this whole thing. I can simply get rid of the j here and j here. I know there's a negative sign, but don't even worry about that because it's magnitude. I can get rid of this e to the minus j beta r because that is a phase, right? And then I can say this sine term doesn't even need to be here, just beta times that. So really what I'm going to do is this. Say it's that times 2 times 21 times 10 to the minus 3. And that should be the value of the total electric field. Could you tell me what that is? 8 is 120 pi, beta is 2 pi over 3. Beta would be, if you don't, beta is 2 pi over lambda, so it's 2 pi over 3. I was
1 milliamp.
1 milliamp. And the rest you're gonna have to run through your calculator.
You got 0.88 millivolts.
Is that what he has? And that's how you do that problem. If I gave them a test and didn't go through this with you, I'm assured, I can almost guarantee that somebody's gonna mess this up in a royal way. It'll be not just a little, because I see this all the time. Agreed? I'm gonna tell you, there are gonna be distances above, if you have a ground plane there, as you move this antenna, where you get perfectly constructive interference, where the electric field will be double the electric field of just one, all right, just a single short dipole, all right? It'll double. And then there will be regions where it'd be actually zero. You follow me? Because you'd have perfectly destructive interference. And what you can think of it is like this. The electric field launched from here, coming down, hits this ground plane, it has a phase inversion, then it keeps going straight up. And if it adds constructively, you can get up to twice the electric field, and if it adds destructively, you get zero. So that's the one thing, when you got a wire over a ground plane, and you're measuring the electric field with that antenna, as you move away, you'll hear peaks, and then zeros, peaks and zeros, peaks and zeros.
What happened to the sine term?
Sine of x is about x for small values. So if you have sine of theta, it's about equal to theta for theta small. And a good question is, what is theta small? My rule of thumb is when you're at theta equivalent to less than about 10 degrees in radians. And I don't know what that is exactly. Pi radians is 180, so pi over 18 radians or less, whatever that is.
Oh, okay.
Do y'all remember that sine of x is about x for small value? All right. I hope this is helpful. I'm trying to prepare you for the test. Next, is there another problem?
Yeah.
Good.
Target received power, determine the single pulse received power level for the target for a radar system having the following characteristics.
And this is radar. And I teach radar, which gain the transmitter. This is my target. Go ahead.
Transmitter, 100 kilowatt peak,
Oh, 100 kW.
frequency 9.4 gigahertz,
9.4 gigahertz.
antenna gain 32 dB,
32.
target RCS 0 dB.
It should be 0 dB SM, right?
Yeah.
That means dB square meters. If it was 10 square meters, it would be 1 dB square meter, because you take, the way you do this is, it'd be 10 dB square meters. You take 10 times the log of the RCS in meters squared to get the value in dB square meters. So if it's 1 square meter, it's 0 dB square meters. Do you understand that? Because the log of 1 is 0. And they say 0 dB SM, and that means that the actual sigma is 1 meter squared. Are you with me? Because anytime you're dealing with dB and it's related to a power term, and it's 10 times the log of sigma, would be sigma dBSM, where sigma would be in meters squared. Okay. Keep going. What else?
Target range 50 kilometers.
Okay, so we have a range here of 50 kilometers. What do they want?
Single pulse received power level.
All right, so they want to know how much power comes back, scatters from here, and then the radar receives. In other words, the power that's absorbed by the radar, or that comes back. So do you remember how to get that? P received. We could go through it. There is a single equation, but we can just work our way through it if you want. Anybody want to start there on this one? Did anybody do this at all?
Wait, what are we looking for again?
The received power back at the radar.
So it hits the target and then that, okay.
So if we wanted that power received back at the antenna, not the power density, but the power, here's how I would start if you don't remember the formula. Start right here and find the actual PAV, right? The average power density, and that would be what? The transmitted power over 4 pi r squared times the gain of the transmitter, the linear gain of the transmitter, correct? Now, once that's going, It comes on and it strikes this and is re-radiated in all directions isotropically, right? So now we multiply this by sigma. Now we have all that, this much power is going to be scattered. And the scattered power, doesn't it fall off as 1 over r squared? Right? You come down with a pulse, bam, it starts falling off, and we assume it's isotropic. So then we divide that by 4 pi r squared again. Now that's the power density coming back, the reflected power density, right? Then it strikes this antenna, and the antenna catches it, I say. It's times the aperture, the area, the electrical area of the antenna, right? And you remember what that is? That's lambda squared over 4 pi times the gain of the receiver. And that would be P received. Y'all remember this? The way I did it before? Class. So now we just stick in the numbers here. But we have 32 dB for that's the actual logarithmic gain. The actual gain of the transmitter would be what? 10 to the 3.2, wouldn't it? Because you would divide that 32 by 10, and then you would take 10 to that power, whatever is the remainder. Are you all with me on this? So we gotta get the wavelength too. What is the wavelength involved in this? 3 times 10 to the 8th divided by 9.4 times 10 to the 9th. That's the wavelength, whatever that is. That looks like 0.03 something.
0.032.
So now you can plug in these values. You notice gain of the receiver is going to be gain of the transmitter, so you can just put a gain squared there and get rid of this back gain. And if you wanted to clean it up, you could put 4 pi cubed here. You could have P transmitter times gain of transmitter squared times sigma over 4 pi cubed r to the 4th, and you would have the P received. You agree with me? What is it? I'm curious.
Really tiny. 2 times 10 to the minus 14.
All right, hold that. Don't get rid of 2 times 10 to the minus 14 watts, right?
I guess 2.1.
What?
2.1.
All right, 2.1. All right, now take this into dBm. It would be 10 times the log of that power, 2.1 times 10 to the minus 14, divided by 10 to the minus 3. So how much is it in dBm?
Minus 107.
All right. Let me tell you something that on the phones, I don't know if your smartphones surely do this, but I don't know how to do it on mine. On the old phones, you could see how much received power you were getting from a tower, and it would be in dBm. Now that's received power that's absorbed, not the total power that's, I mean the power that's usable at the phone. It's not the power, the actual power that's received would be twice that, but only half of that power can ever be used for anything. And I don't know if your phones have that. I'm sure they do. Have you ever looked at
You
this?
used to go into a special code inside of it that you can get to.
Which is interesting about 100 dBm is, or minus 100 dBm is kind of common for the power levels. You get from minus 80 to minus 100 all the time, which is kind of amazing. Your phone can extract data from that signal. And there's a couple ways they do it. One is using something called, it's coherency, where they send the pulse, identical pulses twice, and they add the values. And what happens is the noise floor will always be the same, but the signal will double, or they can send it as many times as they want. That way they can get signal out of noise. All right, is there another one, or is that the last?
What's the last one?
All right, so if you did your homework, you would have done those. And you would have probably found the first one had the wrong answer if you did it correctly.
So
what did you do right here in the last step? I got to the 2.1, so you're just converting it back to decimals?
No, not, dBm.
Decimals per meter?
Not dBm is a power. dBm is power. It's really power normalized to 1 milliwatt. It's called dBm.
Okay.
Okay? All right, now, does anybody have any questions regarding the material? Because we've got waveguides we've covered, we've got antennas, we've got surface reflections, right? We've got fiber optics.
Can we go back to that first question?
Which one?
Because I still think that like,
Okay.
because what it says is consider a lossless half-wave dipole antenna if the antenna is delivered 1 milliwatt to a match.
Oh, delivering. That's, it's not receiving, it's delivering.
Yeah, it's
That's the-
delivering, so you have to find P receive.
All right,
which is where
that's,
that two came into play.
that's completely different. I didn't understand this thing. If it's delivering that much power to the load, it's not receiving it, it's delivering.
That's why I was bringing up that 1/2 P received equation equals VL squared over CZL.
So with a matched load in place, right? So read the problem.
Consider a lossless half-wave dipole antenna if the antenna is delivering 1 milliwatt to a matched load.
That's, stop, that's all I need to. So now they're saying that the load here is actually 73.2, but that's actually minus here. Minus J 42.5 ohms. And this is absorbing right here. P load is 1 milliwatt, right?
Yeah.
Right?
Yeah.
That means it's receiving twice that. You're absolutely right about that. If that's what this problem statement was, it means that the antenna, since it's a matched load, it's gotta be receiving twice that. This means this, P received, is actually 2 times 10 to the minus third watts. If it's received with a matched load, you get half the power out that's received by the antenna. Now, that means for V open circuit, when we draw this, and we say this is plus to minus V open circuit, and then we're gonna have the 73.2 ohms, and then we're gonna have the J 42.5 ohms, and then we're gonna put the actual 10 ohms on here. And they wanna know, they actually want the power, don't they?
Yeah, they will determine the power if the load is changed to 10 ohms.
Alright, so I've gotta get V open circuit, and this V open circuit here would be the square root of 4 times R rad times P received, or P received. And that means V open circuit, I'll get out of your way, it's gonna be square root of 4, 73.2 ohms, and P received is 2 times 10 to the minus 3.
Yeah, so that gives you 0.765.
Alright, after that, we can just calculate the current. This would be IP. And we could say that IP here would be equal to V open circuit divided by 73 plus 10, or 83.2 plus J 42.5. And that's 0.765 for V open circuit. Once we get that number, we can get P of the load equal to 1/2 times magnitude of IP squared times 10. Or really just 5 times IP squared. First, can you give me IP on this one? Magnitude only. I'm not gonna put fiber optics on the test, right? Personally, a lot of stuff in the fiber optics is not based on first principles. It's sort of just technical formulas.
Get like 81.9. Reliance.
Anybody else?
Yeah.
Alright, now what's the power? Let's just take that square and multiply it by 5.
It's 0.336 kilowatts. This should be.
Thank you for making me do it again.
That's what I was trying to get at earlier.
My bad, I didn't catch that word. I was into the mode, it was received, not dissipated, or however they said. Received at the load, or however they said.
Delivered.
Delivered to the load. That was my bad. Okay, but you understand the principles that I'm trying to show you. Alright, now, again, I'm just gonna tell you this, because I got about a little over 10 minutes. Again, for the test, you start back there, wave propagation in free space. We went through it, both time and frequency domain, right? We went through plane waves, then we went through reflections, right? Then we went through, if you think about it, we also went through oblique incidents. Remember that? I'm not gonna give you an oblique incident problem, just for the record. I may on the final, but I'll tell you if I'm gonna, and I'd have to provide you with those formulas, because they're a little much for you to remember, because you don't use them often enough. Then, after that, we had reflections from oblique angles, because we get the Fresnel reflection coefficients. Then we had propagation through lossy media, right? And didn't we do one where we had like a shield? We had a thick piece of material that the electric field came in incident on, and how we had like a piece of material, and we had a field coming in, going through, and then coming out the outside. Did we do that? Remember that? You remember it, yeah. All right. This was in chapter 6. All right. Just take a look at it. After that, then we get into chapter 7, and that's waveguides, and we do rectangular waveguide equations, right? There's 2 modes, TE and TM, right? Okay? Now, I don't expect you to memorize the field equations for either, but you do have to know that for TE modes, the impedance will always be the characteristic impedance of the regions, the A to naught, divided by that square root of 1 minus FC over F squared, right? And for TM, it's the square root of 1 minus FC over F squared times the characteristic impedance. And this is important. When you look at, just to make sure you get the impedance right, you know how to find the fundamental frequency is the 1 ohm mode of a waveguide, rectangular waveguide. And the way you figure that out is that the longest dimension is half wavelength, right? That half wavelength that you figure out will be associated with the cutoff frequency for the 1 ohm mode. Remember this, class? So remember that. With waveguides, we also looked at a waveguide when it was used as a transmission line. Do y'all remember that problem? That was the one I spent some time on. So know that one. Know how to do that one. We didn't look at circular waveguides, and what this book doesn't cover it. I may do that later if we have time. We looked at fiber optics, but I'm not going to test you on fiber optics. That's more of an information item. There's really not a lot you can do with that in terms of a first principles approach. Then after that, we got into propagating electromagnetic fields from antennas, and we talked about short dipoles, loop antennas, half-wave dipoles, and we talked about the gain. We talked about the effect of aperture, right? And we talked about a lot of different problems related to that. Then we talked about monopoles and the effect of a ground plane. We did the horizontal wire problem, but if it was a vertical wire, it would be doable as well. That just means it looks like twice its length, right? Only that the fields don't radiate into the ground plane. So it's the same electric fields as an antenna, twice the length of a monopole would radiate in the upper half. The radiation resistance is halved and the directivity is doubled. Then after that, we did the Friis transmission equation. Do you remember we took energy from one antenna to another? And you had to be aware of the polarization mismatch. And we had to be aware of the fact that if you have 2 antennas like this, both say half-wave dipoles, then you have to actually know that the angle that energy is, or the signal's coming in to that second antenna, because this would be for maximum gain, right? If you hold the separation distance constant, if I move them like this, there's zero field from this one getting into that one. And they're related by what? The angular function squared, right? Really, it would be the cosine of pi over 2 cosine of whatever theta is measured from the z-axis to r squared times the other stuff, the j60i over r. And you have to be aware short dipole and half-wave dipole have different. I'll tell you what, I'll give you the equation for the electric field for a half-wave dipole, but I'm not going to give it to you for a short. You're going to have to know that one, all right? In fairness, I think you should be able to handle that.
For a short.
J a to beta I L e to the minus j beta r sine theta over 4 pi r. I think you can get that one. Hmm?
So we just had one like that.
Yeah, you've had a lot before. We did that. We've had about 5 or 6 problems with that end, so.
So definitely we'll have to know like all of the max directivities for each case.
Just 2 cases, short dipole
Short halfway.
and halfway. For the loop antenna, the directivity is 1.5.
Yeah.
And the gain is the same, it's sine squared theta is the pattern. All right. What else? You don't have to know the impedance or the input impedance of the loop antenna. Yep, I'm going to assume you know the impedance of a exact half-wave dipole, 73.2 plus J 42.5, and for one that's 0.485 lambda, that's only 73.5. Remember, the imaginary part gets knocked off. There's no J 42.5 in it. If you just take a half-wave dipole, just make it a little bit shorter, 0.485 instead of 0.5 lambda, then it gets rid of that imaginary component. And what else?
With the 0.485 lambda, that comes from just shortening the wire, right? Okay.
Just snipping off the ends. Maybe we should do that just for kicks. We might. We'll see how this plays out. Then after that, we did radar, right? Yeah. And since we've done the effects of the ground plane with antennas, you had monopole and we had horizontal problem I just put up there. So you've got that. Now, I was going to get into today chapter 9, but I think I'm going to forego that just because you got this test coming up and you guys aren't going to, I'm going to have to retread this material anyway. Are there any more questions on here? Because I want to take any questions you have. Well, I got you in front of me.
How many questions are on the test?
I always get that. You know, because the problem is I might have 5 problems, and on each problem it'll have multiple answers.
Yeah.
So probably 5 discretely different problems where I ask multiple things on each one,
Yeah.
and that's only fair. So don't. I got one kid, the man, he used to drive me nuts. Would you ask this? Yeah, I could ask that. What did you ask this? That's a good idea. Would you ask this? I think I told you this. It happens every once in a while. And he's like a lawyer trying to figure out where the crime is. And he's looking at me and he keeps going, and the class is really kind of, don't ask him anymore. He's going to put it on me because you keep asking. But he was also, I'm sure you think this way too. I want to calculate my grades, so I want to know what I need to make. Like I want to know what my grade is in the class. And I'm thinking, well, you've got the formula I use. You've got all your quizzes, all your tests. So why are you asking me? You've got to calculate, do the math on this one, or just build an Excel spreadsheet and start putting in your final exam grades to see what you get. But I'm sure you know people like that. And they want to know as much as they can about anything that might benefit them when they should spend all their time studying instead of thinking of how they can, of the score they need to make or how many questions. They need to find out, how to answer the concept questions they're going to be asked. Is there anything else that you want to know? Any questions you got? We covered a fair amount of material.
And do you have those homeworks graded?
Is this the extra credit one? Hold on.
There
I think it was the one before that.
There's one before the extra credit one. There's one before the math.
Which one? I think I've got them. I might have this
The
upstairs.
one before the MATLAB is the first.
What?
Was the one with the,
It's Alexander Cord,
had two angled antennas on it, yeah.
oh, that one, yeah. This is the MATLAB, isn't it? Yeah, this is the Mat.
MATLAB is extra credit.
You know, I may have that upstairs. Would you mind? Can you guys come upstairs with me? We can just break class now. I gotta erase the board. It's about 27 after, and I held you one time for 15 extra minutes or something. I forgot how many. Hmm? You know, but I gotta tell you, I have, in my life, teaching, I found out that summer courses, summer classes, cover more material in less time. And people can absolutely bomb. I mean, you can flunk a summer course blinking. It's so easy if you don't stay up with it. What's that, mini
The
message?
mini masters.
And I don't know much about, I've never taught one, I don't have any idea how the grading is in there or anything like that, but